Hello, my name is Carson Stell, and this is a presentation on quantum security. We're going to be talking about uh, what is quantum security and how does it apply to information security. Really, it is quantum computing and how it can be and will be is already being applied to information security principles. So let's dive into it. Why does it matter? Right now, the current most widely used algorithm for security is RSA, and it cannot be broken. Cannot be broken with classical computers. Technically, it can. It would just take a really, really, really long time. So we say it can't be broken. Uh, and so the security that not just everyday text messages, emails use, but government secrets and things that need protection that are a bit more valuable and classified also use RSA, even if it's higher levels, higher bits. That doesn't really matter when it comes to quantum computing. And yes, as we'll see, there are algorithms that have been produced that a quantum computer could use to break it, just like that, just like that. So as you can see here on the right, here's one of those algorithms that I was talking about, the one that we're going to be looking at. It's called Shor's algorithm. And so on the x-axis, we've got the number of digits. And so it doesn't really care. The more digits you have, it's the computer is only going to use around the same number of operations to break it. And so you may think, okay, we can just crank up that same RSA's digits so that we have the prime factors, just make them a lot larger, and then we've got the product that's much larger too, and that'll be fine. Well, no, that would be safer using a classical algorithm, but quantum computers work a lot differently. Speaking of quantum computing, how it works differently. So just a little refresher. I know a lot of you guys already know this stuff. We don't really need to know it in depth too much for the rest of this presentation. So qubits and bits are not the same thing. Bits exist solely in the two states of 0 and 1, and qubits are also within those two states, but they can also exist within a kind of a mix between the two. So you could have, just for the sake of this example, 0.3 or 0.7. They can exist in both states in different ratios. And so it's not limited to just 0 or 1, and that has a lot of that holds a lot more computational power and a lot more possibilities. There's also entanglement, where you have qubits that are entangled. They are down to a physical level. Their quantum states are linked in a way, and so you could have multiple, let's say, thousands and millions of qubits in a quantum CPU, and one of them it falls, the state falters, or it becomes error prone, and it falls. Well, the other qubits, because they are entangled, are going to keep it in check and make sure it doesn't fall, and so it's actually not only much more computationally powerful, but it's a lot less error prone if you have it under the right conditions, and that's another thing. You have to keep it really, really cold because qubits are fragile, and there are different technologies being developed right now, namely by Microsoft. I've seen a bit on that recently, but there are different technologies being developed to work around that. But yes, quantum computers are extremely fragile. So theoretically, if we can get a quantum computer to exist and to operate in a normal state, the qubits would hold each other accountable. But that is not the case right now. All right, little refresher on RSA encryption. So we take two large prime factors and multiply them together. We can do this almost instantly now. Your phone can do it super quickly. Now it's factoring that large large product that takes much more time. It's much more difficult, and our classical computers of today cannot do it. They can do it. It just takes long time. I believe I saw somewhere, we might have talked about it in class, using RSA 256-bit encryption. Encryption. If you encrypt data with that, it would take longer, and you try to brute force it. If you try to brute force it, it would take longer than the universe has to exist to decode it. And so there's really no point. It's yes, it's possible, but yeah, it's not going to happen within your lifetime at all, or the lifetime of the Earth. So that is why we use RSA encryption, because there is no way that anyone could decrypt it until quantum came along. Womp womp. And so the breaking point comes when Q day will come, Q day will arrive, and we'll talk more about Q day here in a bit. I'm sure you can kind of see where the name came from, D-Day. But this man named Shor developed an algorithm simply to prove a point that when quantum computing comes along, information is going to be a lot less secure. And I think he did a great job with it. As we saw in this slide with this graph, it much more effectively, as we can see here, factors large products. And it can do that that's only possible with the power of quantum computing. Instead of, here's an analogy, if you're going through a maze, instead of having to explore one by one each path, and then you find the dead ends, a quantum computer, using the power of the qubits that exist in the superpositions, can essentially wash over the entire maze. And it's with each of the paths, instead of saying, yes, we're going to this path and checking it out, or no, you can have the computer simultaneously check each of the paths and then attribute a probability for that path being the correct path. And then the correct path, using quantum mechanics, I'm not really sure on all the details behind this. It's way over my head. But the probability of the correct path will essentially resonate, and it will choke out all of the other probabilities for the incorrect paths, and it will compute what is probabilistically what is most probably the correct path to take in the maze. And so it does this the same way with large factors and the product. It washes over the entire, instead of brute forcing each combination, it washes over the entire solution state, all of them, and it it gives what it believes is most probably the correct solution, correct factors. That's the word I was looking for. And so that is how Shor's algorithm works, and that's one example of many different algorithms that people have developed to break RSA. And so he didn't do this to be like, hey, yeah, let's try and get all this information. He did it to prove a point that, hey, when quantum computing comes along, we need to be ready, because the math, there is math that exists and that will continue to be developed that can easily break it. So let's come up with solutions to it. And so if we don't figure this out, which we are going to get into how it is figured out, this compromises a lot of different things in the world. Banking systems can be hacked into. Secure websites become insecure. It's all using RSA. Government communications, they use RSA as well. So that all goes down the drain. And so quantum on the horizon actually hints at potential decryption on the horizon, as we just talked about. That leads us to harvest now, decrypt later. It is where attackers will collect encrypted data today. They cannot decrypt it. They have no idea what it says. But they store all of the encrypted data in large data pools, which is relatively cheap to do. If they have the technology to do so, they can store gigabytes, terabytes, exabytes of data for cheaper than we actually think they could. And they are simply waiting on quantum computers to be able to decrypt that information. which is no good. Government secrets that say the lifetime of a secret being classified is 40 to 50 years. Say that information needs to stay secret for 40 to 50 years. Well, they're using RSA to communicate that classified information. Attackers can store it, and they have the information encrypted. Let's say Q day, which is the day that is coming that quantum computers become available. And they can then use the quantum computing to decrypt using Shor's algorithm or some other algorithm that information. Okay, that let's say that's in 20 years. Well, that the information is now compromised. The government information that was classified, was supposed to stay classified, is now compromised. As we can see here, medical information is also, let's say within our lifetimes, our social security number is floating around online, and we provided it to our bank or whatever else through their HTTPS protocol, and it was secure. Well, hopefully nobody has grabbed that and is sitting on it, sitting on our name and our encrypted social security number and other personal information, because when Q day arrives, they'll be able to decrypt it. Okay, that's all scary. That's no good. What are some solutions? So we've got two here that we're going to go over. Post-quantum cryptography and quantum key distribution. So post-quantum cryptography was designed to resist quantum attacks using advanced mathematics. And so there are some standards that have been made, some quantum standards. This was actually just back in 2024 called crystals Kyber and crystals dilithium. They're being standardized by NIST, and so that PQC can actually be reliable and safe way to defend against when quantum computing becomes readily available. How are we going to protect against it? So there are advanced mathematical algorithms similar to Shor's, but kind of working the other way to keep us safe, to keep the information secure. Now, the drawback to these equations and these functions formulas to keep the information safe, there are discrepancies that can and will be found in mathematical formulas and algorithms. That's the word I've been looking for, algorithms, that could be broken in the future. For example, I believe it was called Psych. There was an algorithm that was developed called Psych, and it was pretty high up on the list for potential algorithms to keep information safe in the quantum age. And there were a group of grad students who actually figured out in about an hour, or they figured out how to break it using math to fight math, using fire to fight fire. And they broke it not using a quantum computer, but using classical computer. Not because of anything special about the computer, but because of a loophole or a discrepancy they found in the mathematical equation. So this is very promising if we can actually find math that holds up, an algorithm that cannot be broken like that. The risk in that is that it does have the potential to be broken down if a discrepancy is found. And AI being developed has the potential to highlight those discrepancies. So a bit dangerous. It's much more cost effective than the next option, much easier to produce, and it's actually probably much cheaper to do research on as well. So this is looking like a good potential for keeping us safe against the quantum age security. Next option is quantum key distribution. Now, quantum key distribution uses quantum physics for secure key exchange through fiber optics and different quantum channels like that. The sender will send photons that are sent through a filter, and the filter is randomly switched between horizontal, vertical, diagonal. So it's sending these photons that are polarized differently, and they are received by the receiver, who is randomly receiving all the photons, but randomly depolarizing them. He's making guesses for whether it's horizontal, vertical, or diagonal. So he's only receiving part of them. The ones that were not depolarized were lost. Their state fell. I can't remember the exact terminology for that. But yeah, their position collapsed. That's what it is. And so because the photons that they were already entangled with are still with the cinder, the ones that were that collapsed are collapsed. So both the sender and the receiver still have the intact non-collapsed photons. So that provides a key that only the sender and receiver have, that is dependent on the quantum states of the photons, the particles themselves. And so when an attacker observes or tries to observe the states of those photons, of those particles, it collapses. As you know, with quantum computing, if you observe something, it collapses. It completely changes the state when you observe it. And so when it's been observed, it changes, and there's actually a way to alert the sender and the receiver both when that change happens. And so they're like, if someone observes it, they're instantly alerted of it. So it's really secure. There's no way to break it. However, there are a few drawbacks. It's really, really, really expensive. Like, how would you give everyone a photon beam and then a receiver? And then you've got those fiber optic cables or whatever other methods you could develop of quantum transmitting those. So far, they've only tested it. They tested it. It only works up to a few hundred kilometers. Like I said, it requires that special hardware. You can also easily do a denial of service attack. There's this thing called, I think it's the wrench problem. If you find the quantum channel, you find the fiber optic cables, you just tap on it with a wrench. That essentially tricks the system into thinking that it's been observed, and it will collapse. And so that makes it to where neither the sender or the receiver could use those keys anymore. So it's really easy to mess up if you can't observe the information that is being transmitted. So it's secure in that way, but denial of service attacks would be really easy because of how fragile the systems are. And so you've got these two options, right? PQC, post-quantum cryptography, with the math that's cheaper but less reliable. Then you've got quantum key distribution that is much more expensive and hard to produce, but it is infinitely reliable. It cannot be broken. So if we can find a way to make this cheaper and to where you cannot hinder the information, you can't falsely tamper with it or do a denial of service attack, this would be the way to go for sure. But as it stands, those are the differences between them. And so, yes, for security, let's not get all caught up in the detriments, right? It can be scary. Quantum random number generation provides true randomness, or at least a lot closer to random than current computers can. That will provide us with better simulations for cyber defense, improved anomaly detection, because, think about it, with viruses and anomalies, say malware, in the quantum age, if it's using AI and quantum computing, you could have malware that is injected into your system that is constantly adapting to changes that are being made. And it, just like a real biological virus, it adapts through generations, or even in a singular generation, it learns the defenses that are being put up on your system. It can actually jump over those. And so, yes, that is a threat that quantum and AI teaming up could pose with that malware, but the defenses will be equally as powerful. If QKD works out, then this will not be a problem at all. And so, with all of this, there is an inevitable global quantum race going on right now. It's a nation-state competition for who can achieve quantum computing first. Who will break the encryption first? Because whenever they do break it, whatever nation breaks it first, they're not going to publish a paper about it, probably. They're going to keep quiet as they silently in the background begin decrypting information from other nations. So that will quickly create a power imbalance between countries. Yes, and that will give an intelligence advantage for whichever nation gets it first, or nations. That will give the potential for infrastructure attacks and mass surveillance and huge financial disruption if say in the crypto market, people's private keys are decrypted. There you go, millions, billions of dollars drained. So that's dangerous. As we talked about Q-Day earlier, Y2Q is the year that, or it's essentially whenever the first country breaks it, and so that that's another play on Y2K if you can't tell. Whenever the first nation breaks quantum computing and is able to do that, it'll be silent, it'll be in the background, but it'll have huge implications. So there is a race for that. So all of that, yes, it sounds very scary, and it is, but luckily there are many limitations that are stopping it from happening right now. Quantum computers are still in development, like we were talking about earlier. They're unstable, they're fragile. Error-free qubits don't exist yet, but with entanglement, theoretically, that would be very secure and awesome. But error-free qubits, because of how fragile they are, it's not looking too good so far. And it's not at the scale that they exist. The biggest ones, I believe, are only a few hundred qubits. I think there might have been some recent developments that have broken that, but still not even close to breaking RSA at the scale they're at. They would need millions of qubits running stably and error-free. That being said, there is still an urgency. The transition to post-quantum computing is already underway. People are developing those algorithms to stay more secure. The reason I'm giving this presentation is to urge us to yes, let's actually let's be even more ready. Okay, it's coming faster than we think. The current experts believe that Q-Day, Y2Q is going to be sometime in the 2030s, in about 15 years. 10 to 15 years is what they said. So that's sooner than I think a lot of people would hope. So we should be ready. And I think we are going to be ready, honestly. Data today may be vulnerable tomorrow. So let's... that's with the harvest now decrypt later thing. If we can find a way to encrypt it better today, have dual encryption, push that more, that's better. In conclusion, yes, all these threats are real, they're upcoming, but it's nothing to sweat about right now. But it is good that we are already starting to work on things like on PQC and QKD. Yes, the future of security is changing. Before we wrap this presentation up, I would like to give you listeners a hypothetical. The day is coming, say, when QKD is developed, when, based off of the laws of physics, it is impossible to break the security. Okay, is that a utopia or is that a dystopia? One in which hackers cannot at all get into a system where, yes, government agencies' information is secure, but so are threats. It's impossible to penetrate that. White hat hackers are now obsolete. Is that a utopia or is that a dystopia? There are definitely advantages and disadvantages to it. So that's just something to digest and ponder on for you. So these are my resources. Thank you for listening, and have fun listening to the rest of the presentations.